So welcome to this pre-recording of lecture 37 on symbolic computation. So throughout this course we have been using SageMath. Today we will look into SymPy. So SymPy is one of the packages incorporated in SageMath, but one can use SymPy also directly from within Python. So there are some features in SymPy that are not as well elaborated in SageMath, and I will give some examples of this. But in this first slide presentation, I will try to indicate the most important aspects. And then in the second part, I will demonstrate with the Jupyter notebook. Okay, so here is the logo for SymPy. It is a project that has many developers and has been developed for more than a decade, almost 2 decades right now. SageMath uses an enhanced Python, so everything gets pre-parsed. Symbolic, one can do with SymPy, one can do symbolic computation in pure Python. So one can extend the Python interpreter with SymPy. So the homepage the homepage of the project provides installation instructions for this. SageMath is a very huge project. In contrast, SymPy is very lightweight. If you want to do only particular symbolic computation manipulations, then SymPy might be a better match than SageMath. For its multi-precision arithmetic, it depends on MPMath. One does not need to install. One can use it in an online cell, very similar to the Sage cell server. It is a free library. SageMath is licensed under the GNU GPL license, which means that modifications must be made public. This is under the BSD license. This is not strictly required, or this is not required. So these are kind of the important differences. So one can do this purely from within Python, or a Jupyter notebook with a Python kernel, Python where the package SymPy is installed. It installs rather quickly because it has not only one dependency, and then the license is also more permissive than SageMath. Okay, we do symbolic computation, and when one does symbolic computation, one computes expressions, and one starts with a symbol or a variable. So both SymPy and SageMath use the same syntax to declare symbols. Often, if you really want to use a feature from within SageMath, so SymPy series from within SageMath, then you must explicitly declare the symbol to be of the type of SymPy's type. We will illustrate this when we look at series. So this is to start from within a Sage session doing some computations with SymPy. Afterwards, one may have to cast the results from SymPy into SageMath, and this can happen via the symbolic ring. Okay, so why would we be interested in explicitly using SymPy? consider Taylor series. So this is a copy from a slide that I presented earlier in this course. So you can see the general formula for a term in the Taylor series. So going from one term to the next essentially means that you take one extra derivative, you divide by k plus 1, where k plus 1 is the next term, and you multiply with x minus a. So there is a three-step general method to go from one term to the next. So one can therefore quite straightforwardly define a generator, as is done in SymPy. So the series, if you compute a Taylor series, you can truncate it. You could see Taylor series as a truncated polynomial. That's actually what SageMath does. But that requires you that you set the order from the beginning. With a generator, you can be more relaxed and compute the next term in the series. With SymPy, we can also solve recurrence relations. So recurrence relations are very useful in the analysis of algorithms. So in some sense, this goes into the discrete math part. When you examine a sorting method, for example, merge sort has the cost that is expressed here with a one-term recurrence relation. Solving this recurrence relation, so it's a one-term recurrence relation because you need one initial condition, and you see that at the left and the right you have one call to the cost function capital T. Solving this relation will lead into the 2 log of the dimension. So this is one way to prove that merge or sort is logarithmic in the dimension. We encountered the Fibonacci numbers, and the Fibonacci numbers satisfy this two-term recurrence relation. We can compute, by solving this recurrence relation, we can compute an explicit expression, explicit in n, for any number, for any Fibonacci number. And this involves the golden ratio, which is interesting. It's a very interesting connection between the golden ratio, the geometric ratio, which I showed in one of the animations, and the Fibonacci numbers. Okay, so the purpose of this lecture is to indicate how SymPy is useful. SymPy is extremely useful, either as a standalone Python package or as a Python package in SageMath. Okay, so to demonstrate this, let me flip to the Jupyter notebook. So flip out the slides. I have a SageMath notebook prepared, but in order to make this a little bit more dynamic, I will create a new SageMath notebook, or a new Jupyter notebook with a SageMath kernel. So in this lecture, we will use SymPy in SageMath. So I was perhaps a little bit too quick, but in my installation I also can run the Jupyter notebook with a Python 3 kernel, and perhaps I should demonstrate this. If I do this, then I can import SymPy. So I'm in a regular SymPy session, and I can declare a variable I can import or I can take the Taylor series, so the series, the SymPy series of the square root of 1 minus x expanded around 0, and for the number of terms I'm going to provide none, n equals none. So I'm confusing the syntax. So for the square root, I have to say that I'm explicitly using the SymPy. And the type of my t is a generator, which means that I can do a next and a next. And let's do the next 8 times. So this will give me the 8 next terms in the series. So I should save this. So this is SymPy in a plain Python session. So with the Python interpreter extended with SymPy. And this is already illustrating one of the features of SymPy series, is that one can ask for the terms in the Taylor series expansion one after the other. One can also replace the n with a number here, but by saying n equals none, one creates a generator. Okay, so let me now illustrate this also in a Jupyter notebook with a SageMath kernel. So this is already lecture 37. In a markdown cell. So let me illustrate the previous computation, how to do the series expansions. So what's the difference? So let me illustrate before we get into the series expansions. Let us see the difference between symbols in SymPy and symbols in SageMath. So in order to use SymPy explicitly in a SageMath session, I have to do the same as within Python. So I'm going to declare the variable x, and let me ask for its type. Then you see that it is indeed a symbol, but then of the SymPy. If I do this directly in Sage, so let me use another letter, y, then I get a symbolic expression. So if I are calling the square root on this, so if I do, so let us see what happens. So if we call the square root of SageMath on both symbols, we will get expressions in SageMath. So let me illustrate this. I'm running the square root of x and I'm asking for the type. So x is a symbol that is of SymPy, observe that if I would do SymPy square root of x, that then I have a different object. So this is important. In a way, this goes back to what we have seen in the beginning of the course and also what holds for Python. So every object belongs to a class. And the type of methods and the type of operations that can be done on the object depends on its class. There are certain things that one can do on a SageMath object, an expression, that one cannot do on a SymPy expression, and the other way around. So where is the distinction very important? So the distinction between SymPy expressions and SageMath expressions is very important with the generators on series. So here, what is the question now? What is the problem? So I demonstrated it already, but let me now phrase it as a problem. So compute a generator for the series expansion of let me typeset it in LaTeX, of the square root of 1 minus x about x equals to 0. So this is the problem that we will consider. Let me start from scratch here. So I'm going to reset. I'm going to declare, so I have to import SymPy, and let me do this step by step. Declare the variable x as a variable, as a SymPy symbol. Then I have my expression, so I will have f as a SymPy square root of 1 minus x. And then I have my series of f at x, and then n equals none. So let me see what I compute with this. So series is not defined. That is because I did an import, not from SymPy import series. And you see S is a generator object. And now I can ask for the next term in the series. I can compute the next term in the series. And let me now do the next terms, the next 8 terms. And here you see the series expansion, the terms in a series expansion as a list. Okay, suppose now I want to turn this list into a SageMath object. So very good. What do I do with this? Well, one has to be a little bit careful now because it is in that list, but I did not assign it to anything. So the list is there. If I'm going to reassign this, I'm going to run next again. So that's kind of uncomfortable. Let me backtrack therefore. So I'm going to reset. So let me backtrack. So what I want to show now is how to turn this into a SageMath object. So let me get the first 10 terms. So this returns the list. So this is a Python list. Okay, what is my problem now? Convert the output in L to a SageMath expression. Okay, so the first thought that we would have would be to take the sum and indeed what comes back is the sum, the Python sum, but what comes back is an expression of the SymPy. So the sum is something that works on any Python list, but the sum was executed via the SymPy expressions. So let me illustrate this. So let me document this. The sum L was executed via the SymPy arithmetic. So via the symbolic computations defined in symbol, and on return we obtain an object of SymPy core.add. So it is not properly in SageMath yet. If you want the SageMath expression, so then you have to convert to the symbolic ring. And you see that the output looks differently. The type is also now of a symbolic expression. So what did we do? We converted the SymPy object into a SageMath expression via the explicit cast, via the cast into the symbolic ring via the SR. So this is important. Let me indicate what happens if you would not do this. So you can see that we can still continue this. So these statements here, they still work. So we have the next terms in our expansions. Observe that we still have, or I did a reset. So observe that the above way of working would not work on SageMath variables. So if I have y is now a SageMath variable, if I would do the SymPy series, and if I would do also the SymPy square root, but now everything on y, then at first it appears that I do have a proper generator, but you see that the generator is of little use. So I actually have only one term, and that only gives me the expression back. So this is something to be aware of. So working with SageMath variables, even if you put them through the SymPy functions, it will still not work as intended. Okay, so here is an application, and I will copy this for so as an application of this next term and of the series, we can compute the Catalan numbers via a generating function, via the Taylor series of a generating function. And also the Fibonacci numbers have a generating series for this. So let me copy and paste from what I have prepared. So here you see the generating function of for the Catalan function. X is still a variable of SymPy, and you see if I now work with this, the next function works on the generator object. And Catalan numbers are so important that they are predefined. So what are the Catalan numbers? The Catalan numbers are these coefficients in the Taylor series expansion. Okay, so that's already half of what I wanted to illustrate. Another feature which is better elaborated in SymPy than in Sage is pattern matching. So I did not allude to this in the slides. So what is the problem? Consider the expressions 10 times x to the power 3 and y times x to the power 3, and compute a match between those two expressions. So the two expressions are definitely different. So one is a monomial in one variable, the other is a monomial in two variables. But you see that there is a match. So the match between the two is the y which can be mapped, or which can be matched to 10. So let me illustrate how this can be done. So I will reset. From SymPy, I will import the symbol and then the wild for the wild card. So X is the symbol and Y is the wild card. Now we can do the matching between the expressions. So typically in general, I would also type in a new variable for the expression. But since it is so short, I can type in everything as is. And now the D should be a dictionary, but the D remains empty, so perhaps I did something wrong. So I must have imported everything. So let me reset, declare the symbols again, and then one sees the matching. So I thought that I would follow a more better practice, but one must, in order to see the dictionary with the matching, we must import everything from SymPy. But the point is that the dictionary encodes the matching between the constant 10 in the first expression and the y in the second expression. So this can be useful in a substitution where the two expressions become identical if one substitutes the key by the value. Okay, so then the last part in this demonstration is the solving of the recurrences. Consider the Fibonacci numbers. So the Fibonacci numbers are the solution of a two-term recurrence. So we have f of n is the sum of the previous values. And this actually only works if n is larger than 2 or equal to 2. The first two Fibonacci numbers are 0 and 1. So we use the Fibonacci numbers to introduce memoization. We can solve this recurrence relation with SymPy. So let me reset and import the function. So the function is with a capital. So I'm declaring f as a function. So the functions that we used in SageMath were defined with little f. So here we are using capital F. So I will define the Fibonacci equation first in terms of the n. And the way I'm writing this down is a little bit different from what I defined in the recursion. So I have not yet specified the two terms recursion, but in a symbolic solver we can solve this symbolically already. So I will solve for the function. And now you see that I have a family of two functions. So we obtained a parameterized family with two constants, with two general constants sitting in there. So in order to make, so we've seen the symbolic solution has two parameters which will be determined with the, or they will be determined by the initial conditions. So the same thing that we have seen with differential equations, where we have a second order differential equation. And we will provide these two initial conditions by a dictionary. So I will provide the dictionary conditions. And add this to the solver. So we have a particular solution, which is actually the Fibonacci numbers. So I will call them Fn. So I will solve the equation for Fn, but give the initial conditions. And here you have it. We have the general explicit expression. We have the explicit expression of the Fibonacci numbers for any n. Now this looks a little bit awkward at first. Why? Because the Fibonacci numbers are integers. And you see the square root of 5 sitting in there. Actually, you recognize, or perhaps not, the golden ratio is in there as well. So this is a very interesting connection. So the point that I actually want to make is that you see that this is still an expression of the type that is of the SymPy type. So in order to use the result in a SageMath session, we must convert, or we must cast Fn into the symbolic ring. Okay, so then let's do this. Then you see that the type is a symbolic expression. Now, symbolic expressions are callable, so that's another interesting feature. So symbolic expressions are callable in SageMath, which means that you can treat them as functions. So I can explicitly ask what are the variables in this expression, and you see that n is one of the variables. So, what can I do with this now? I can evaluate, say that I want to have the third Fibonacci number. And here it is, the third Fibonacci number in all its full glory. But let me try to expand this or simplify this. Then one will see that this gets gradually simplified to an integer number. So here you see the opposite of expressions, well, an expansion that leads to a simplification. So to end, let us look at the first 10 Fibonacci numbers. So, and call this into a list comprehension. And here it is without the simplification. Doesn't look like integer numbers. But let me, I was too fast. Let me do the simplification via the expand. And here we recognize the first 10 Fibonacci numbers. Okay, so this is a very short overview of SymPy. You certainly, we have introduced ourselves through symbolic computation, through SageMath in this course, but one can redo most of it, almost all of it, through SymPy. So one can now work backwards and look at the various chapters within SymPy. So that is it. I'm now thinking about still some other feature, so I will leave off with a note. I will not demonstrate it, but you can find it in the lecture notes. One other feature also exported in SymPy is the PSLQ algorithm to find the nearest algebraic number to a given floating point number. So this brings us all the way back to the beginning of the course when we introduced algebraic numbers. We saw that working with a symbolic factorization went through the computation of the declaration of new numbers. So the square root of 2 is actually a symbol, and one can extend the rational numbers with the square root of 2. One can also take an approximation of the square root of 2 and find the perhaps I will do this. So if I have the square root of 2, so I'm improvising a little bit, so so I have the square root of 2, and I can do the SymPy PSLQ of 1 and S2, and I did not import SymPy. And I should have prepared this better, but the PSLQ algorithm is definitely available from within SymPy as well. So, and it should be available also within Sage. Okay, search the documentation for SymPy. So that is the next step that one should do now, which I will do. Because I'm curious. And this is the unscripted, unprepared section in this course where I probably must have misremembered, so this is rather embarrassing, but I will prepare this better in the lecture, and I will sign off here. Thank you for watching. Nevertheless, I hope that this was interesting.